Hi folks, we're going to take a look at page 378, number 15, and they're asking us to prove this, this equality here. All right, so I take a look at the two sides, and definitely the left-hand side looks like it's a little more complex, so probably offers more opportunity to do some algebra. So I'm going to start with the left-hand side. Problem is that there's not really much algebra we can do here. I mean, I guess we could break this up as magnitude of u plus v times magnitude of u plus v, but there's no way to sort of separate out this sum of vectors, which is inside a magnitude, and separate them out. And we look on the right-hand side of the equation, we see that the magnitude of u, magnitude of v are separate. Okay, so we need to find another way to do some simplification here. And this is where I want to remind you of one of the properties we found for dot product. Okay, and one of the things we saw is that if I take a vector and I dot it with itself, well, that just gives me the magnitude of p times, again, the magnitude of p. So that would be the magnitude of p squared. Okay, so notice the squares on the outside. So first I find the magnitude, then I square it, and then times the cosine of the angle between them. But since it's the same angle, the angle is 0. Cos of 0 is equal to 1. So this is one of the key properties we found for the dot product. So I'm going to apply that here. I'm going to take a look at this. I'm going to think of u plus v as a single vector. If I've got its magnitude squared, that's equivalent to the vector dotted with itself. So in other words, this is equivalent to the vector u plus v dotted with itself. So dot u plus v. Okay, but by writing it in this format, now I can use the fact that I have a distributive property for the dot product. Okay, and I'm going to do the same thing with the second expression. I'm going to write that as u minus v dotted with itself. Whoops, u minus v. And same thing, I now have access to the distributive property. So that's going to do next. I'm just going to distribute. So again, we saw that we can do this distribution just as though these were two binomials, except instead of regular multiplication, it's dot product. So this is going to give me u dot u. Okay, then u dot v. Okay, then v dot u. And then lastly, v dot v. Okay, and now I'm going to do the same thing here. So it's going to be plus u dot u. Okay, here minus u dot v. Then minus again v dot u. And then lastly, it's going to be plus v dot v. And maybe you can already see where this is going. So before I even start to simplify, I don't even really need to, because I see a u dot v minus u dot v. And here I see a v dot u minus v dot u. So they just cancel out completely. And then I see that I've got two u dot u's. Okay, and then here I also have a v dot v plus v dot v, so plus 2 v dot v. Okay, but let's keep in mind that property we just talked about, a vector dotted with itself is just equal to the magnitude squared. So this is just equal to 2 times the magnitude of u squared, and this is 2 times the magnitude of v squared. And then, lo and behold, that's exactly the right-hand side of the equation, which I was trying to prove. Okay, so it is proved. So just to recap here, this is one of those properties that you're going to want to keep in mind. Okay, that if you have the magnitude of vector squared, it can be rewritten as the vector dotted with itself. Or of course, the other way around, if you dot a vector with itself, it's equal to the magnitude squared. So in other words, this is one of those important properties that you're going to want to know. Okay, that's it for this one.